Good morning to my panel. My name is Roobemalan A. Thiruchelvan. My supervisor's name is T.S. Dr. Saifuddin Hafiz bin Yahya. Today, I would like to present my PSM2 project named A Tailpipe Design in Exhaust System using High-Profile Curve Definition. In this video, I would like to present the objective, problem statement, methodology, results and discussion, and also conclusion. Okay, moving on to my next slide. Okay, what is exhaust tailpipe? Exhaust tailpipe is actually the very end part of the exhaust system in a vehicle where the exhaust gas exits. Then, in order to improve the performance of the exhaust tailpipe, I will need to use the high profile curve definition, which is a Bezier curve, which helps me to design the curve in a controlled manner. Which there is several types of curve, but I will be using the C to C straight line curve transition in order to improve the design. So this actually helps to increase the performance of the tailpipe even further. For objective is to increase the performance of exhaust tailpipe using the high profile curve definition for the improvement design. Next is to analyze both models using the method of analysis. And the last one will be to validate both models with the support of coefficient of variation and also design of efficiency. Moving on to the problem statement. The problem statement is by Shin 2009 states that the right shape of exhaust tailpipe, diameter of inlet of the exhaust tailpipe, number of inlets and outlets, size and weight, and also the material used will affect the performance of the exhaust tailpipe. Moving on to Cruz in 1997, he states that if we don't use the Bezier curve properly, can result in crowding and also sometimes actual occupation of adjoining lanes, which will decrease the performance of the exhaust tailpipe. And the last problem statement is actually to develop a research methodology in order to design an exhaust tailpipe. Next will be methodology. Methodology consists of design modeling, linear static analysis, fatigue analysis, and also dynamic analysis. For design and modeling, we use the SolidWorks. By using the C-shape transition curve, we were able to improve the design, as you can see for the improvement design. You can see the 2D and the 3D drawing here. After drawing the designs in the SolidWorks, is that we then use the SolidWorks simulation software in order to mesh the designs, both the designs. So you can see the existing and design improvement design there on your right. And the meshing type was actually detail type mesh, and then the mesh I used was there, and the Jacobian points are high quality mesh, and then the max element size, minimum element size, mesh quality, the total knots, and also the elements. In the SolidWorks, the boundary and loading conditions was actually fixed, where the fixed point was actually placed in the very initial point of the exhaust tailpipe, and for the loading condition was placed right at the tip where the exhaust gas will be coming out. As for stress and displacement distribution, after setting the boundary condition, later on the pressure was chosen as the force to react on the existing and also the improvement design. So then the data was recorded and the pressure was increased from 1 mega Newton per meter square till 20 mega Newton per meter square. And then the maximum one-way stress and the displacement was recorded. So after collecting the data, we will then calculate the fatigue analysis. So first we will be calculating the safety factor, which is the yield strength of material over maximum one-way stress. Then next we will be using the Newton interpolation polynomial in order to calculate the exact stress when the material was undergoing failure, which is the safety factor at 1. And then after that, we'll be using the values for both the improvement and existing design, then we'll be calculating the design of efficiency. So moving on to dynamic analysis, we'll be using the Ansys FLUENT software. As you can see, in the FLUENT software, there will be a meshing software in order for you to mesh the existing and also the improvement design. Then after you mesh the design, is then placed into the Ansys result software in order for it to in order for you to place the load, which is the input velocity and also the outflow. So the initial part will be putting the input velocity, as you can see in the existing and improvement design, and the outflow you also can see and the existing and the improvement design. So after setting the boundary condition, the initial velocity was chosen as the airflow velocity and the data was recorded as the initial velocity increased from 100 meter per second to 1000 meter per second. Then the maximum velocity, pressure and the eddy viscosity was obtained. After getting the data, we'll be calculating the coefficient of variation, which is standard deviation over mean times by 100%. As you can see from the example in the bottom with the existing and improvement, then the mean, standard deviation and also the coefficient of variation. This is in order to check the accuracy, stability and the consistency of the data. So moving on to results and discussion. So starting with the static analysis, you can see the 1 mean stress graph where the improvement existing design results were plotted. So when the pressure was 3 mega Newton per meter square, the maximum 1 mean stress for the existing design was 1.152 giga Newton per meter square compared to the improvement design, which was 0.1384 giga Newton meter square. Therefore, the stress on the existing design is higher than the improvement design. So next it will be the displacement graph where both designs were plotted and where the pressure at 3 meganewton per meter square existing design is at 157 centimeters, but the improvement design was at 92.4 millimeters, which shows less displacement for improvement design. So moving on to safety factor, which clearly shows that when the existing design is only safe to be used when the pressure is at less than 3 mega Newton per meter square, whereas the improvement design will be able to use when it's less than 19 mega Newton per meter square. Using Newton interpolation polynomial, we found that the existing design will undergo failure when the stress increases more than 2.318 mega Newton per meter square compared to the improvement design, which is 19.07 mega Newton per meter square. Using this value, we calculated the design of efficiency, which was 801%. The velocity graph where both designs are plotted, and when initial velocity is at 400 meters per second, existing design has a max velocity of 488.05 meter per second, and improvement design was 648.12 meter per second, which shows more velocity for the improvement design. Next is a pressure graph where both designs were plotted, and when initial velocity at 400 meter per second, existing design has a pressure of 41,635 Pascal and improvement design was 5,770.49 Pascal, which shows less pressure for improvement design. Moving on to the eddy viscosity graph where both designs were plotted, and when initial velocity is at 400 meter per second, existing design has an eddy viscosity of 0.07262 Pascal second, and improvement design was 0.0542 Pascal second, which shows less turbulent flow for the improvement design. So moving on to coefficient of variation. As you can see, this determines the smoothness of the curve, which is lesser the percentage, the smoother the curve. So since the improvement design has lesser percentage in all velocity, pressure and also eddy viscosity, so it clearly shows that the curves in the improvement design is much more smoother. So based on the study shown, we can clearly see that there's increase in performance from the existing to the improvement design in all aspects, which is from the static analysis and also the dynamic analysis. And for the design efficiency, which clearly shows that there's an improvement of 801% better than the existing design. And the coefficient of variation shows a lower percentage in all aspects, which in return shows a smaller, smoother curve.